Welcome to our Artificial Intelligence through Artificial Intelligence YouTube channel and to the Introduction to Deep Learning with PyTorch course. In video 13, we explained the vanishing gradient problem in simple terms, avoiding complex math. Now let's dive deeper. This time with the mathematical intuition behind it. Similar to video 13, we will analyze a 3-layer neural network, 2 hidden layers plus 1 output layer, using sigmoid activation. We will follow this approach. First, we will compute the activations at each layer during the forward pass. Then, we will calculate the gradients during the backward pass. Finally, we will analyze the computed gradients to show their impact on the learning of a neural network. Ready? Let's decode the math. Suppose the chosen 3-layer neural network has input x 0.5 weights, W1, W2, W3 all initialized to 0.5, biases, B1, B2, B3 all set to 0, target output T 0.8. Let's first understand what happens during the forward pass. Starting from input layer to hidden layer 1, the input x equals 0.5 is multiplied by the weight W1, and the bias B1 is added to perform the calculation. This result is called the weighted input, denoted as Z1, which in this case is 0.25. Next, the sigmoid activation function is applied to Z1. The output of this activation, known as the activation output and denoted by H1, is 0.562. At layer 2, the network multiplies output of the layer 1, 0.562, by a weight W2, 0.5, and adds bias 0, giving 0.281 as weighted input. The sigmoid function is applied and at the weighted input resulting 0.570 as activation output. At the output layer, the network multiplies layer 2 output, 0.570, by weight W3, 0.5, and adds bias 0, giving 0.285 as weighted input. The sigmoid activation converts 0.285 to 0.571 activation output. This is the final output of our neural network, which needs to be minimized during the backward pass. The next part of the video explains this process in detail, highlighting how the vanishing gradient problem occurs. Now let's see what happens as we go back from output layer to input layer for updating weights and biases to minimize loss. Processing in a neural network from output layer to input layer is called as backward pass of a neural network. During this process, we aim to update the model's weights by calculating how much each weight contributed to the overall loss. As previously described too, all weights will be 0.5, all biases will be set to 0 and our target will be 0.8. Let's start from the output layer. Here, we will compute contribution of weight W3 in the loss. 3 mathematical expressions we'll use to calculate this contribution. See here first expression, which is used to calculate error, means difference between predicted value and the target. This shows the change in loss or derivative of loss with respect to output. Our prediction was 0.571, but our target or the desired output was 0.8, so the error is minus 0.229. The objective of backward pass is to minimize this error. Let's say it expression 1. The second expression calculates the gradient of the loss L with respect to the weighted input Z3 at a neuron in the output layer. Specifically, this gradient is obtained by multiplying output obtained in expression 1, here, minus 0.229, with the derivative of the activation output at that neuron, obtained during the forward pass, here, 0.245. This product, approximately minus 0.056, reflects how sensitive the loss is to small changes in Z3. In the third expression, to compute how the loss changes with respect to the weight W3, we apply the chain rule again. We multiply the gradient, actually the output obtained in expression 2, by the activation output H2. This is actually an output from the previous layer, which in this case is 0.570. This yields -0.032. In simpler terms, this tells us that to reduce the loss, we should adjust the weight W3 by approximately -0.032. These calculations illustrate how backpropagation systematically determines the appropriate updates for each parameter in the network based on the flow of gradients from the output layer backward through the network, ultimately enabling the model to learn. Here, we move back and figure out how much the activation H2 in the second hidden layer influenced the final loss. Let's write the mathematical expression to calculate this influence. We use the gradient from the output layer, -0.056, computed using expression 2, and multiply it with the weight W3. This tells us how strongly the loss is affected by H2, which comes out to -0.028. Let's say it expression 4. Now we see how the weighted input Z2, that is an input obtained before applying the activation function at hidden layer 2, affects the loss. This is done using expression 5. We multiply the result, obtained in expression 4, which is -0.028, by the derivative of the activation function, sigmoid in this case, which is 0.245. The result -0.0069 shows that the influence is getting smaller. It may be called as expression 5. Finally, we calculate how much we should update weight W2 using expression 6. We multiply the gradient, obtained in expression 5, by H1, which is an activation output from hidden layer 1. The very small value, -0.0039, indicates that the earlier weights are barely being updated, as evident from the increasingly smaller gradients observed in the second layer. Put simply, to reduce the loss, the weight 2 should be adjusted by approximately -0.0039. Moving back from output layer to input layer, at the earliest layer, that is hidden layer 1, we find out how much the activation H1 influenced the final loss. Starting from expression 7, we use the gradient from the next layer, that is hidden layer 2, and the output of expression 5, -0.0069, and multiply it with the weight W2. This small negative gradient, -0.0035, suggests H1 slightly increases the loss. See here how the weighted input Z1, that is an input obtained before applying the activation function, affects the loss. We multiply the result obtained in expression 7, which is -0.0035, by the derivative of the activation function, sigmoid in this case, which is 0.246. The result -0.0086 shows that the influence is getting smaller. We may call it expression 8. Finally, we calculate how much we should update weight W1. We multiply the gradient, obtained in expression 8, by the input 0.5. The extremely small value, -0.00043, indicates that the update to W1 is negligible, illustrating the vanishing gradient problem. Gradients become progressively smaller as we move backward through the network layers. So, let's analyze the gradients from the output layer back to the input layer. At the output, the gradient was -0.032. One step back, at hidden layer 2, it decreased to -0.0039, and at hidden layer 1, it further dropped to -0.00043, almost vanishing. That wraps up today's video. Please don't forget to subscribe our channel, like the video, share, and comment it to stay updated with this series.